Hi, everyone, and welcome to our continuation on Chapter 16, Communication. So today we're going to talk about digital communication. So an information signal that is going to have same variations with time as the information itself is known as an analog signal. So for example, I'm using a microphone right now to speak, and the signal voltage that's produced by a microphone is analogous to the sound wave that falls on the microphone, right? So the voltage output from the microphone is an analog signal. Now, most of the information that we're going to transmit and communicate is going to be analog in nature. Speech, music, a picture on a television, that's all analog. When any signal is transmitted over a long distance, it's going to pick up some noise, right? Noise is not just unwanted sound, but it's any unwanted random signal that adds to the signal that is being transmitted. Also, the power of the signal is going to become less. So we will say that the signal has been attenuated. So what this does is, for long distance transmission, the signal has to be amplified at regular intervals. The problem is that on amplification of an analog signal, you also amplify the noise. So you might have, let's say, the analog signal might look something like this, right? You have voltage here, and you have some time over here, and you have the signal that looks maybe something like this, right? And when you transmit it, it's transmitted, right? The signal might actually end up looking something like this. So you can see the almost shaky nature of it is because you have noise getting added to it, and the amplitude is not quite so high because it's getting attenuated, right? It's losing power over time. So now what happens when you amplify it? So this triangle symbol is for what we call a repeater amplifier. So what happens when you amplify it? I'm going to use a different color now to denote this. So when you amplify it, basically you're not amplifying this, you're amplifying this. And what it ends up looking like is the original shape of the curve is going to be, reproduced somehow, but it is extremely, extremely noisy. It'll end up looking something like this. So now this is where we can talk about digital signals. So in contrast to an analog signal, a digital signal is going to be a series of highs and lows with no values in between the highs and the lows. It's essentially, the data is getting transmitted as a particular sequence of highs and lows, or effectively a sequence of ones and zeros. The signal will still suffer from noise and attenuation, but when you amplify it, the noisy ones and zeros can be regenerated or reshaped to return the signal to its original form. And as a result of that, you can restore the signal. So let's say, for the sake of argument, that your signal is going to look a little bit like this, right? So let me use a different color here. Let me use green. So your signal maybe looks something like this. So it's either on or it's off, right? That's what your signal looks like. Well, what happens when you start transmitting this signal, right? When you transmit the signal, well, remember it's I beg your pardon. It is still going to get noisy because noise is any random unwanted signal. But now that random unwanted signal is going to look a little bit like this, right? Might look something like this. So we now can put in what we call a different type of amplifier, and this one is called a regenerator amplifier. And what it'll end up doing is it's going to reproduce our original signal quite effectively without any noise being present or amplified. So unlike an analog signal, a digital signal can be transmitted over a long distance with regular regeneration without the signal becoming degraded. What we're also finding is that the modern digital electronic circuits are in general more reliable, and they are cheaper to produce. So in the future, we think that the vast majority of communications are likely to be digital. Another advantage of digital systems is that you can add extra information, extra data to the transmissions. So these extra data are a code for the receiving system so that the transmitted signal may be checked and corrected before the signal is fully reproduced. So let's look at how exactly you would transmit a digital signal when you have an analog input. Let's have a look at that. So think of an analog signal like speech or music. When you're using a microphone, the generated voltage is going to vary continuously, right? So if you want to do a digital transmission, you need to convert this analog signal into a digital signal. And what happens is you use something called an ADC, which is simply an analog to digital converter. So how does this guy work? Let's have a look. Converter. We are going to sample the analog voltage at regular intervals of time. What that means is we're going to see what the voltage is at regular intervals of time. We're not continuously measuring it. We're going to measure it at certain frequency, which is called the sampling frequency or the sampling rate. The value of the sample voltage that you're measuring each time is converted then into a digital number, a binary number, which is going to represent the voltage value. Now, I'm not going to go through what a binary number is. I'm assuming that you know this. If you don't, I would suggest looking at your math courses and to how in terms of how to determine how to write a binary number. But a binary number, very briefly, consists of a number of digits, and we call those digits bits. And all the binary number that are shown here are going to be 4-bit numbers. So for example, if you have a decimal number 0, it's going to be written as like that. If you have, let's say, what's a good one to look at? 7, let's say. You can write it as that in binary, in base 2 numbers, basically. So larger numbers, obviously are going to require digital numbers with more bits. So I'm not going to get into that. Or if you have 700, I'm not going to try and write that here. But for the purpose of our discussion and what you're going to see in your examinations, you should be able to get away with numbers that are, 4 bits or less. What you also want to know is when you're reading the number, the binary number, the bit on the left-hand side of the number is called the most significant bit, or the MSB, and this is called the least significant bit, or the LSB. So now assume that a 4-bit number is being used, then you are going to sample the voltage. So let's say you have voltage which is 5.0 volts, right? You're going to write that in binary numbers as 0, 1, 0, 1. The important thing for you to know is that you would write, even if it was you can only go up to the whole number in this case, right? So when you're trying to sample, let's say you had 5.4 volts, you would still only write that as 0, 1, 0, 1. So you get to the whole number below the actual value of the sample voltage. Now, I would say let's have a look at an analog signal and see how we can convert that into some digital numbers. So let's say you have a sinusoidal signal as an analog signal in the upper graph, and we've been sampling it at a rate of 10 kilohertz. So the lower graph should tell you, so this is your signal voltage, and I'll write this piece here for you. So this is our signal voltage, and this is the sample voltages. What would they look like if we actually write these out? So these are discrete numbers, right? And I'll use a different color for this. These are going to be discrete voltages altogether. So what do you think these are going to be? Well, so our first one, pretty clear. It's going to look like something like this. It's an individual kind of voltage that you're going to see, right? So you're going to see a you're going to see a 7 here, you're going to see a 9 there, you're going to see like a 10 there, and then you're going to see an 11 maybe up there, and so on. I'm just going to quickly write all of these out for you. So these are your individually measured voltages at discrete moments in time, right? Now you need to convert them into digital signals. You have to convert them into binary. So the first guy is going to become simply this. The second guy is going to become that. The third guy, 1010, 1011, and so on. So I just wrote all of these out for you. So after this digital signal has been transmitted, so the red indicates your digital signal, right? This is one piece of the digital signal. Once you've transmitted this signal, it gets converted back into an analog signal using a digital to analog converter, which is basically the reverse of the analog to digital converter. So what would that analog signal look like once you have recovered it? And you're going to find that the analog signal is very grainy. It consists of large steps, and the size of these steps, and hence the faithfulness of the reproduction of the initial analog signal, it can be improved by using more voltage levels and by sampling much more frequently. So let's look at what this recovered signal is going to look like. So this is what your recovered signal is going to look like. As I said, very grainy, lots of step changes. So if you want to increase, and I'll write this down again for you, if you want to increase the quality, I guess, of the signal, the faithfulness of the reproduction, you need more frequent sampling, right? So that will reduce the kind of the graininess of this of this guy. More frequent, not frequency, I beg your pardon, frequent sampling, and you need to have more voltage levels. So rather than sampling only, like at individual discrete 5, 6, 7, 8, 9 volt levels, you need to go even lower than this. So the number of bits in each digital number is going to limit the number of voltage levels that you can have. So I'll say limited by number of bits. So in this example, I had 4 bits, right? So in practice, you really need 8 or more bits for sampling. And an 8-bit number is going to give you 256 levels. So I'll say in practice, need 8-bit sampling. So the greater the sampling frequency, the more faithful your reproduction will be of the original signal. So, for example, for good quality reproduction of music, the higher audible frequencies need to be present, right? So frequencies that are up to about 20 kilohertz. So on CDs, for those of you who know what CDs are, the sampling frequency is actually 44.1 kilohertz. And this quality of reproduction is not required for speech, and it would prove very costly. In a telephone system, which is where speech is going to come into play, the sampling frequency is about 10 kilohertz. And the highest frequency that we can transmit over the phone is about 3.4 kilohertz. So that, folks, is how you would convert from, actually transmit the signal going from analog to digital and digital to analog. So I'll see you in the next video where we're going to talk a little bit more about the relative merits of the different channels of communication you have. So, we're going to talk about wire pairs and coaxial cables and so on. So I want to talk a little bit more about what the different merits are of the different methods of communication. So I'll see you in the next video. Thank you.